The ambiguous case of the sine rule. So watch this video if you've already watched an introductory video on how to use the sine rule in trigonometry. And the word ambiguous means having or expressing more than one possible meaning. So it could mean more than one thing and we're not initially sure about it. So from our last video on this, we're looking at typically non-right angle triangles such as triangle ABC here. Okay, and remember our conventions for naming angles and sides of triangles. We remember the development of the sine rule tends to be in that form if we're looking for side lengths, but it doesn't have to be in that form. It can also be in that form for angles or side lengths. Okay, so that's from the previous video. We noticed that one of the contexts suitable for the use of the sine rule was using the sine rule to determine angle sizes. Okay, it can be used for side lengths, but to use the sine rule for angles given two sides and a non-included angle. So the angle, it might be corresponding, it might be angle B for a given side B or something like that, but it's not an included angle, so it's not sitting between two known sides. We're looking at a GeoGebra demonstration by this author here called Mr. Hardman, and he, assuming it is a he, has created a very usable and useful application which I graciously will make use of here. So just acknowledging the author there, and let's have a look. So we're looking for angle B. Okay, you can read there in the triangle ABC we're given side length A is 6.8, side length B is 13, and angle at A is 30.1, which you can hopefully see on the diagram in front of you. We have to find angle B, which we can see there in the right hand bottom corner with a theta on it. Using the sine rule, we could set up the expression there, sine theta over 13 equals sine 30.1 over 6.8. Rearranging, we can isolate sine theta, and then taking inverse sine of the result, we get 74.4 degrees, and you can check that with your own calculator. Fantastic, we've got an answer, and that's that. No, it's not that. Have a look at the angle. The angle here is clearly greater than 90 degrees. It's obtuse. Yet we have an angle of 74.7. What gives? Okay, how has this occurred? Is there something gone wrong? Does this math not actually work? Have we been fooling you the whole time? Is it all a conspiracy? If you've said yes to that last one, you need to go away from my YouTube channel. But basically, we look at another case, how this could be constructed otherwise. All right, and this is where the ambiguous situation can arise. One of the answers could be 74.4, but I can't justify that based on that diagram. How does a 74.4 occur too is a reasonable question. Okay, so thanks to the author of this GeoGebra application, we can see an alternative here. Now we generate an imaginary circle or a circumference around. We can see that with angle A maintained at 30.1, so that means this line AB and out to the red section beyond the right of point B is horizontal according to the screen, and the other side of the triangle stays 30.1 degrees apart from that. And we can see that 74.4 is actually that angle there, and we can show that mathematically as well. So that's the 74.4. It doesn't relate to that diagram, but it is a possible solution. Okay. The calculator always chooses the smallest of the two possible answers. Now, I've just said two possible answers. That's true. There are two possible answers. First way of justifying that is by looking at the diagram, and for the dimensions and the angles of the triangle to stay as they are, we would have to have this 30.1 degree angle maintained, as I said before, and that would mean that the other alternative would be to have another 6.8 line, an alternative one coming down here. And we note that this and that are the same length, of course, because we need a side length of 6.8, and that's an isosceles triangle formed in there. So what we have is 74.4 here, but also here. Now the line passing through point B right through it there creates a straight angle, and so the angle sum here must be 180 degrees. So theta is 180 degrees, take away 74.4. That will give us theta. So there are two solutions, okay? That's one way of justifying a solution, using isosceles triangles. Another way is using the unit circle, which hopefully you're familiar with. So the angle for theta that we want is, as I said, 180 take 74.4, which is 105.6. So we need to check whether the angle you want is acute or obtuse based on the diagram, if you have a scale diagram, but that might not always be the case. Alright, so we need to look at this a bit more. And by the way, I said there was a second way of justifying that second angle. If we have 74.4 there, in quadrant 1, we can also have, due to the symmetry, in quadrant 2, another 74.4 in there, in that acute angle there. And the overall angle itself would be 180 take 74.4, and then we have that same value as that we had by showing it with isosceles triangles. So putting all this together, we want to determine when to use the ambiguous case of the sine rule. When do we need to look for a second answer? Or if we have to choose between the two answers, how do we generate both answers so that we've got some way or some information to base a decision around? Okay, now if the given angle is obtuse or a right angle, then there is only one such triangle. Our given angle was 30.1 degrees, and so that's not obtuse and it's not a right angle. So we did have to actually search for two answers or check that out. So so because our given angle was acute, we had to check that out. So that makes this point here important. As a rule of thumb, it's definitely worth checking that out if the given angle is acute. Alright, so we're looking at this otherwise, and that's the case we just looked at. It wasn't obtuse, it was acute because we had angle well and truly less than 90. It wasn't obtuse, nor was it a right angle, it was acute. Okay, so an acute given angle, and that's when you check the presence for the other case, and we're going to look at that now. Instead of deriving it purely mathematically, we're going to look at how to actually go ahead and do that. I'm going to use this example here. Use the sine rule to find the magnitude of angle xzy. So that's this angle here at z. Alright, I might just be cruisy and treat that as the symbol angle z, just like that. Alright, so we're going to look at angle z, and we're given angle y is 25 degrees, you can see there, and side y is 5 there, and side z is 6 centimeters there. Okay, so we're looking for angles, so we might set up the sine rule such that we have sine z over z equals sine y over y as such. So rearranging, we have 6 sine 25 over 5, and entering that in the calculator we have 0.5071. 5071 to 4 decimal places. Okay, I'm just doing that to maintain some reasonable precision there. Okay, so to get Z, we would go inverse sine of that answer. And on our calculator, I've got 30.47 degrees on my calculator. Okay, 30.47 degrees to 2 decimal places, which for me is fine. 30.47, yep, okay. Now we've had a diagram, there's no scale diagram here. The given angle, well, what was the given angle? Yes, it was acute, look. Alright, so it was an acute angle, so we need to check for the presence of the other case. Okay, so let's do that. Now, what it's going to look like, there will be another case, is here's the diagram, look. So basically we've got two Z's possible, the 30.47, and look, there's another Z, one Z there and another Z there. This is the other one if we drew it differently. So let's compare the original drawing. Okay, we've got that there, and we had 5 and 6 centimeters there, which that's that there. The answer we gave wasn't actually for the suitable for the diagram given. Alright, I guess we could have used, even though it's not a, well, we can assume perhaps it's not a scale diagram, that does look obtuse, doesn't it? Okay, so, well, it depends, you know, is that a good diagram or not? Is it meant to be, or is it meant to be a guide only? If it's meant to be a guide only, you say there are two possible answers. If it's for this and it's to scale or in proportion, well, you could say the answer is the obtuse answer. So whether you're finding the two possible answers or finding the answer that is suitable for a particular diagram, the process is the same. So that is a valid answer, but not for that diagram, it seems. So the other one would be, or more suitably for this diagram, okay, so more suitable for that diagram, assuming the diagram's any good, sometimes they're not, okay. We have Z, angle Z equals 180, take 30.47 degrees, okay, and that's where the 149.53 comes from. 149.53 degrees is the more suitable angle. The ambiguous case of the sine rule applied.